Good evening, everyone. So today in this lecture, we'll be discussing about the Amperes circuital law, right? The last lecture, we discussed about the Vedavaag law and all its applications, right? So in the last lecture, we discussed about magnetic field due to finite current carrying wire, right? We also discussed about the magnetic field due to circular loop, right? And then we discussed different cases of the finite wire, right? There was a case of what we call as infinite wire, right, carrying current I, and semi-infinite, right? So there were different cases that we discussed in the last lecture, right? And then we discussed about the current carrying loop also, right? Magnetic field at the center of a current carrying loop, right? So, and we also did a general discussion over the magnetic field due to an arc subtending an angle of alpha, right? Subtending an angle of alpha with the center of that loop, right? So the result was mu naught I alpha upon 4 pi r, right? That was the result, right? Now there are few cases here, right? You can see on the screen, right? There are few cases. In the last lecture, we discussed about the general magnetic field calculation. So it was actually mu naught I alpha upon 4 pi r for this arc subtending an angle of alpha with the center, right? But now let's discuss these special cases, right? So these special cases, you can see, yeah, you can look at all these cases. There's some current I is entering the loop, right? These are three different loops, right? One is the circular loop, another is triangular loop, and the third is square loop, right? So some current I is entering the loop, and the same amount of current is actually leaving the loop also, right? So this is actually a symmetric system, right? It's a symmetric planar loop, right? And if some current I is entering the symmetric planar loop and the same current I is leaving the planar loop, right? Then the total magnetic field at the center of this symmetrical planar loop will be always zero, right? It will be always zero because through different junctions, you can see here in this case, this is the point P, right? This is the point P, from where the current actually enters the loop, right? Current actually enters the loop, right? And this is the point C at which the current leaves the loop, right? Now you can see that through different paths, through this path, the current has a different resistance to face, right? And through this path, the current has altogether a different resistance to face, right? So this path will be of a shorter, this path will be a shorter resistive path, right? Shorter resistive path, right? So the resistance for this path will be smaller, right? So that the current through this path will be larger, right? And through rest of the path, the current will be different. So overall, what's going to happen at the center, right? At the center, you can see that this arc will make a larger angle, right? This arc will make a larger angle at the center, right? This alpha is larger, right? Then this angle, right? Then this angle, right? Then this angle. So it means that the last time what we did is that we calculated the magnetic field as mu naught I alpha upon 4 pi r for the circular loops, right? For the circular loops. So here alpha is greater for this arc, but the current is less for this arc, so that the total magnetic field actually becomes equal to the magnetic field because of this arc and the magnetic field because of this arc, right? So they actually become equal, right? So this is how the current distribution takes place between the two arcs of this circular loop, so that the net magnetic field at the center becomes zero. So be it any symmetrical planar loop with a uniform wire, right, made up of uniform wire, then the magnetic field at the center of that symmetrical planar loop will always be zero, right? So here at the center, the B net magnetic field, B net will be equal to zero, right? And same will be the case for this triangular loop as well. The net magnetic field at the center will be equal to B net will be equal to zero, right? And for this case also, net magnetic field will be equal to zero, right? That will be equal to zero. So the magnetic fields in case of symmetrical planar loops, the magnetic fields at their centers will be always equal to zero, right? So it has a zero magnetic field. Now let's move on to the next concept, right? The next object here. We calculated the magnetic field due to a circular loop at the center, right? But now we want to calculate the magnetic field on the axis of this current carrying loop, right? On the axis of this current carrying loop. You can see that in this picture, in this diagram, we have a current carrying loop in which a current I is flowing, right? In which a current I is flowing, right? And it is of a radius R, right? It's placed in this fashion, right? And there is an axis passing through the center of this circular loop. That is what we call as axis of this loop. And at any point on this axis, at any point P on this axis, we want to actually calculate the magnetic field due to this current carrying loop, right? So what we'll do is that we have to apply a Biot-Savart law, right? And we know that Biot-Savart law is nothing. The magnetic field dB at any point is actually given by mu naught I dl sine of theta upon 4 pi r square, right? Upon 4 pi r square. So this is the magnetic field given by actually Biot-Savart law, right? So this is the magnetic field given by Biot-Savart law. So we can calculate the magnetic field using the Biot-Savart law. So let's try to apply the same Biot-Savart law on this circular loop also on its axis, right? So what we'll do is that we'll just choose an elemental current, right? Let's suppose this is the element current here at the top of this ring, right? At the top of this ring. The current I is flowing through this element and dl is the length of this element, current element, right? And if you want to find the magnetic field due to this current element, right? Magnetic field due to this current element. So because of this current element here, which is at a distance of r, right? At a distance of r from this point P, this will be the direction of the magnetic field dB, right? If we use the right hand thumb rule, right, to calculate the magnetic field because of this current element, then this will be the direction. This will be the direction because of this magnetic field created by this current element, right? Similarly, if we take another element, if we choose another element, right? If we are choosing another element right here, this is the another element, dl element, right? And we want to calculate the magnetic field because of this dl element also at this point P, then this will be the direction of the magnetic field, right? And this will be the direction of the magnetic field at this point P, right? And the magnitude of the magnetic, since this is a symmetric loop, right? This is a symmetric loop, right? Circular loop is a symmetric one, right? And they are opposite to each other. Both these elements are actually opposite to each other, so that now the magnitude of these both these field because of these current elements will be equal actually, right? But the direction is different, right? But the direction is different. Let's suppose this is the angle phi here. We're assuming that this is the angle phi here, right? Which the dl element makes with this point P along this axis of this ring. This is phi. This angle will also be equal to phi, right? And if this is phi, then this is dB. We can resolve this dB vector. We can resolve this dB vector into two components, right? We can resolve this dB vector actually into two components. One component will be along y-axis, that will be dB cos of phi. Another component will be along x-axis, that will be dB sine of phi. And same goes with this dB magnetic field here. So one component will be dB cos phi, another component will be dB sine phi. You can see there, you can clearly see that there are two components, right? There are two components, right? There are two components here, which you can see clearly that the two components, this is the one component, right? This is the one component. And this is the another component here, right? This is the another component here. This is the another component here. The two components actually cancel out each other. It means that the vertical components cancel out each other, right? Cancel out each other, right? Or we can write it mathematically that integral of dB cos phi, right? Integral of dB cos phi is nothing. That's actually equal to 0, right? Integral of dB cos phi is actually 0 because each and every cosine component of each and every element, right, is actually cancelled out, is actually vanished, right? Gets vanished. If we choose an element here, right, here, then its cos component will be actually cancelled out by the cos component of this element, right? Similarly, the cos component of this element will be actually cancelled out by the cos component of this element here, right? So it means that overall, since this is a symmetric loop, right? The cosine component of each and every magnetic vector because of the current element will be actually equal to 0, right? Will be actually cancelled out. That's why we write here integral of dB cos phi is actually equal to 0, right? So it means actually it will be only sine component, right? dB sine phi, that will actually contribute to the total magnetic field here, right? Total magnetic field here at this point P. Let's try to calculate that total magnetic field at this point P now, right? So actually B now will be actually the total magnetic field will be now actually dB sine of phi, right? dB sine of phi, correct? Now what is this dB? dB we can write actually using the Amperes law mu naught I TL sine theta, right? Now the question is what is the sine of theta, right? You can see that this dB is actually out of the plane, right? And this is in this plane, dl vector is in this plane, and dB is out of the plane. It means dB will be always perpendicular to this line, right? So that sine theta will be equal to sine 90 degrees. So we can write mu naught I dl sine of 90, right? Upon 4 pi r square, right? So sine of 90 is nothing. So dB is equal to mu naught I TL upon 4 pi r square, right? Now we can substitute the value of dB in the above equation, right? We get the P net as P net is the net magnetic field. It will be integral of mu naught I TL, right? Sine of phi, right? Sine of phi upon 4 pi r square, right? Upon 4 pi r square. Now what is the sine of phi? If we calculate the sine of phi from this equation, it will be actually it will be r upon small r, right? Sine of phi will be actually equal to capital R upon the small r, right? Where capital R is the radius of this ring, right? We can write here capital R is nothing, it's the radius of a ring. Radius of a ring. So capital R is the radius of a ring and small r is the distance of this TL element from this point P, right? We can substitute the value of this sine phi in this equation. Can substitute the value of the sine phi in this equation. We get P net as equal to integral of mu naught I TL sine phi r upon r. So it will be 4 pi r cube, right? 4 pi r cube. Now this mu naught I upon mu naught I r upon 4 pi r cube, right? Integral of dl. Now what is this integral of dl? Is actually the circumference of this circular loop, right? And the circumference of this circular loop is nothing. It's equal to mu naught I r into, that's the 2 pi r, right? Upon 4 pi r cube, right? 4 pi r cube. So pi and pi will go, right? We'll be left with 2 here. So finally the result will be B net is actually equal to, now finally it will be mu naught I, right? R square upon, so it will be r square upon, it will be actually 2r cube, right? And r is nothing, r is actually under root of r square plus x square, right? R square plus x square. So you can write here 2 times r square plus x square raised to power 3 by 2, right? Raised to power 3 by 2. So this is the net magnetic field. So B net is nothing, it's mu naught I r square upon 2 times r square plus x square raised to power 3 by 2. So this is the net magnetic field, right? This is the net magnetic field on the axis of this ring, right? This is the net magnetic field on the axis of this ring having a current I flowing through it, right? I is the current flowing through this ring. So this is the net magnetic field, right? So The final result we got is P net is actually equal to mu naught I r square, right, upon 2 times r square plus x square to the power 3 by 2, right? This is the final result, right? This will be the final result. Now let's suppose that we want to calculate the magnetic field at the center of this ring, at the center of the ring. So at center, the value of x will become 0, right? Value of x will become 0. So x is equal to 0 at center. So it means that our B magnetic field, BC, that's the magnetic field at center, will be mu naught I r square upon 2 times r cube, right? Now this r square and cube will go and we'll be left with mu naught I upon 2r. And same is the result we actually calculated yesterday also, right? The magnetic field at the center of a ring is actually mu naught I upon 2r. So this is the magnetic field at the center, right? Magnetic field at the center of a ring, right? This is the magnetic field at the center of a ring. Now we can also reframe this equation in this manner, right? We can also reframe this equation in this manner, right? So let's suppose our B is actually P axis. We can write it as P axis, right? That's equal to mu naught I r square upon 2, right? 2 times r square plus x square to the power 3 by 2, right? 3 by 2. We can, if we multiply, if we just take r square common from this equation, right? Mu naught I r square. If we take r square common from this equation, right, it will be 2 times r cube here, right? 2 times r cube multiplied by 1 plus x square upon r square, right, raised to power 3 by 2, right? Now this r square and cube will get cancelled, right? It means we can write p axis as mu naught I upon 2 times r 1 plus x square upon r square raised to power 3 by 2, right? So this is the magnetic field. And we know that mu naught I upon 2r is nothing, that's actually equal to magnetic field at center, right? Magnetic field at center. So we can replace it with the magnetic field at center. So we can actually get the relation between the magnetic field at center and the magnetic field at axis. So B axis is nothing, it's actually B center upon 1 plus x square upon r square raised to power 3 by 2, right? So this is the relation between the magnetic field at center and magnetic field at axis. So magnetic field at axis will be magnetic field at center upon 1 plus x square upon r square to the power 3 by 2, right? So this is the relation, right, between the magnetic field at center and the magnetic field at axis, right? So we can write it like this also. Now let's try to calculate different cases also, right? Let's suppose that let's discuss case 1, that case 2. Case 1 we discuss the magnetic field at center. Case 2 is that what is the magnetic field when x is much greater than actually r, right? When x is much greater than r, then what happens to the magnetic field, right? Let's try to calculate that also, right? So we know that B axis is nothing. B axis is actually equal to mu naught I r square, right, upon 2 times r square plus x square to the power 3 by 2, right? When x is much greater than r, right? X is much greater than r, right? We just take x square as common from this equation. Let's take x square as common from this equation, right? In the denominator, mu naught I upon r square 2 times. If we take x square as common from this equation, we'll be left here with x cube only, right? X cube only 1 plus, right, r square upon x square, right? R square upon x square raised to power 3 by 2, right? Raised to power 3 by 2, correct? So it means that if x is much greater than r, right, then x square will be very much greater than this r square, right? or we can say that r square upon x square, will be approximated to 0, right? It will be approximated to 0, right? And we'll be left with b axis as mu naught I r square upon 2 times x cube. Or we can say actually b axis at a larger distance is actually inversely proportional to the x cube, right? It's inversely proportional to the x cube, correct? For the larger distance. And for the smaller distance, actually this magnetic field is a uniform magnetic field when it's very close to the center of ring, right? We'll discuss that case also, right? Now let's discuss the case second. Case third. Case third is that x is much less than r, right? If x is much less than r, or we can say r is much greater than x, then in that case p axis will be equal to mu naught I r square upon 2 times r square plus x square raised to power 3 by 2, right? Raised to power 3 by 2. Now what we can do is that since the condition is that x is very less than r, that means that we're calculating the magnetic field very close to the center of this ring, right? We're calculating the magnetic field very close to the center of this ring, and at the center we know that magnetic field is mu naught I upon 2r, right? So it means that we'll just take r square as common for this equation. R square as common, right? So if we take r square as common, we'll get here 2r cube, right? 1 plus x square upon r square raised to power 3 by 2, right? Raised to power 3 by 2. Now we can neglect this term, 1 x square upon r square with respect to this, right? So we'll be left with only 1, right? We'll be left with only 1. So it means it will be almost approximated to, right? So it will be equal to mu naught I r square and cube will get cancelled. Mu naught I upon 2r, right? Mu naught I upon 2r. So it means that very close to the center of this ring, the magnetic field will behave like a uniform field, right? Very close to the center of this ring, the magnetic field will behave like a uniform magnetic field. Or we can say that very close to this ring, the magnetic field lines will be almost parallel to each other, right? They will be actually almost parallel to each other, right? So let's try to plot the magnetic field at the center of this ring, right? If we do approximation to this equation also, right, we can rewrite this equation also like this, right? So you can actually take mu naught I upon 2r here, right? Taking this term into the numerator, right, we'll be left with 1 plus x square upon r square raised to power 3 by 2, right? Raised to power minus 3 by 2. Let's approximate it doing a binomial approximation here, right? We'll be left with 1 minus 3 upon 2 x square upon r square, right? So this will be the behavior of this magnetic field, right, near the center, right? Or we can say that we can also say that if we approximate this term 3 upon 2 x square upon r square almost equal to 0 as compared to this one, we can say that it very closely behaves like a uniform field. It very closely behaves like a uniform field at the center of this ring, right? Very closely behaves like a uniform field at the center of this ring. And when we do the experiments to find the magnetic field lines near the center of this ring, they almost behave like a parallel lines. They almost behave like a parallel lines near the center of this ring, right? So these are the magnetic field lines because of this ring, right? So there is a circular loop, right? The magnetic field lines are entering, right? These are closed loops, right? So this side will be the north pole, right? This will be the north pole and this will be the south pole, right? This side will behave the north pole of this loop, right? And this side will behave like a south pole of this loop, right? So the conclusion here is that when x is very much greater than the r, right, at larger distance as compared to the center of this ring, right, then there is a cubic behavior, inverse relation with the x, right? So the magnetic field at x-axis is actually inversely proportional to the cube of this distance from the center, right? And similarly, when we calculate the magnetic field very close to the center, right, it almost behaves like a uniform magnetic field, or we can approximate it to a uniform magnetic field. It behaves like a magnetic field lines behaves like a parallel lines, right? And the relation becomes near the axis, near the center is mu naught I upon 2r 1 minus 3x square upon 2r square, right? Now this is the plot, right? This is the plot between the magnetic field due to ring on its axis, right? You can see here the magnetic, if we check the variation of the slope at the topmost point, right? This is the point, this is the point, right? This is the point where x is actually 0, right? X is actually 0. Or we can say this is a point where actually the center of a ring lies, right? This is the ring, right? This is the ring here, and this is how the current flows through the ring, right? And we can see that here at a larger distance, it's inversely proportional to the cube of this x, right? It means that it will it will almost very in a lesser time it will fall for a very smaller distance, right? Or we can say for a very small distance, right? Greater than this distance r by 2, right? It falls, the graph falls actually very quickly because there is a cube here, right? There is a cube here, right? So it falls very quickly because of this cubic equation here, right? Cubic behavior in the denominator, right? So you can see on the left hand side also it is falling very quickly, right? Or we can say the slope actually falls very quickly, right? And at the center of this ring, you can see that if we take the 2 points at the vicinity of the center of this ring, right? 2 points at the vicinity of the center of this ring, you can see here actually it behaves like the slope at near the center of this ring is actually the same. It behaves like the same as the slope is at the center of this ring, right? We know that at the center of the ring, magnetic field is a constant, right? It's a constant magnetic field if the radius of a ring is constant, right? So this is the magnetic field at the center of this ring, that's P naught. But very close to this center of this ring, you can see that there is not much variation in the magnetic field, right? There is not much variation in the magnetic field. It's a very small variation, right? It's a very small variation because one one is actually much greater than this greater than this term, that's 3x square upon 2r square, right? So it means that variation in the slope of this curve near the center of this ring will be very small, right? That's why we can see that the magnetic field lines near the center actually appears to be a parallel field lines, right? The reason is that slope variation is very small, or we can approximate variation to be equal to 0, right? But this is the actual variation that up to first term, magnetic field is actually B naught times 1 minus 3x square upon 2r square, where B naught is nothing, is the magnetic field at center, right? Field at center. So you can see how actually the magnetic field lines behave, right? So this is the graph uh, near the center, right? This is how the behavior of this magnetic field lines to ring near the center is, and this is how the behavior of the magnetic field lines at larger distances is, right? So the curvature actually changes at each and every point, but near the center, the curvature does change very slowly, right? The curvature changes very slowly, right? Now let's try to solve some of the questions related to it. A coil having n turns carrying a current I as shown in the figure, right? The magnetic field intensity at point P is, right? Once again, what you can do is that uh, we have to find there are n turns in this coil, right? So it will be a magnetic field because of each and every coil will be added to the net magnetic field at P, right? Or we can just use this formula, right? Bx axis, we'll be doing it n times, that's mu naught I r square, and we'll multiply it by this factor n if n number of loops are there, right? And divided by the factor 2 times r square plus x square raised to power 3 by 2, right? Raised to power 3 by 2. So this will be the magnetic field at axis, right? We can substitute the values here. X is given as 4, right? Just put the value of x here, 4. So it will be mu naught I r square n upon 2 times r square plus 4 raised to power 3 by 2, right? So this is the magnetic field at this point P. It's a very straightforward question, right? Now let us look at this question. The question is radius of a current carrying coil is r. The ratio of magnetic field at axial point, which is 3r distance away from the center of the coil to the magnetic field at the center of the coil, right? We in the previous slide, right? In the previous slide, actually developed a relation between the magnetic field at center and the magnetic field at an axis, right? You can see here, this is the relation. So actually the B axis is actually B center upon 1 plus x square upon r square raised to power 3 by 2. We can use this equation directly here. So equation we'll be using is B x-axis is actually B center upon 2 times. Is there a factor of 2 or not? No, there is not a factor of 2 here. So it will be BC upon 1 plus x square upon r square, right? Raised to power 3 by 2. And we have to find the ratio of magnetic field at a axial point, which is 3r distance away from the center of the coil to the magnetic field at the center of the coil. So we'll be calculating B axis upon P center, right? B center, that will be equal to 1 upon 1 plus x square upon r square, right? Raised to power 3 by 2. Now the value of x is given here in this equation. In this question, the x is given as 3r from the center, right? Let's just substitute the value of 3r in this equation. We'll get the ratio B axis upon B center, that will be equal to 1 upon 1 plus 3r square, that will be 9r square upon r square, right? Raised to power 3 by 2. So it will be 1 upon 10 raised power 3 by 2, right? So this will be the ratio. 1 upon 10 raised power 3 by 2 will be the ratio for the magnetic field at axis, right? And the magnetic field at the center of this current carrying loop. Now let's discuss about a very important law, right? Which is a very important law for the calculation of magnetic fields, right? Due to symmetric systems, right? That's the Amperes Circuital law, right? Amperes Circuital law. We'll be discussing the Amperes Circuital law and its basic applications, right? For the calculation of the magnetic field due to different shapes, right? So previously we discussed about the Vedavaag law, right? That with the help of that Vedavaag law, we also calculated the magnetic field due to different objects, right? And here Amperes Circuital law is another method, right? Another way of calculating the magnetic field, right? Magnetic field at some points, right? So let's see what actually Amperes Circuital law states, right? So if we calculate a line integral of magnetic field, line integral of a magnetic field along any closed path, right? Line integral of a magnetic field along any closed path, right? That's always equal to mu naught, that's the permeability, times the current enclosed by that closed path, right? So we can rewrite this law actually as integral of, it's a closed line integral, right? Integral of B dot dl, right? B dot dl. That has to be equal to mu naught times the current enclosed, right? Now the question is that what is this closed line integral, right? Let's suppose if we integrate some quantity with respect to this line, right? We integrate some quantity with respect to this line from A to B, right? You can see that this line actually does not form a closed loop, or we can say that this line actually does not enclose any area, right? It does not enclose any area. If somebody will ask you what is the area enclosed by this line A to B, area enclosed is actually 0. Area enclosed is 0, right? Area enclosed is 0. But let's suppose, if we close this line, right, like this, then there is definitely some non-zero area enclosed by this line. So it means that closed lines always enclose some area, right? So that's what we are talking about, the closed paths, right? So closed paths always enclose some area. Similarly, we have closed volumes, right? A closed surface, right? closed surface in case of Gauss law we discussed, right? It was applicable for the closed surfaces, right? We applied that for the closed surfaces, right? That was a surface integral, right? Because that's we took only those surfaces which actually enclose some volume, right? So you can see here these open lines actually does not enclose any volume, and the closed lines, open lines does not enclose any area, right? And the closed line encloses definitely some area. So we'll be applying this Ampere's circuital law for the calculation of magnetic field lines, magnetic field on a closed line, right? So it actually states that, let's suppose you can see we have a closed line here, and there are different currents flowing perpendicular to the plane of this line, right? And some current are flowing out of this plane and some current are flowing into the plane, right? You can see that the dot representation is for the current flowing out of the plane and perpendicular to the plane, right? And the cross representation is for the current into the plane, right? Some currents are enclosed by this loop and some currents are outside this loop, right? The magnetic field at some point, right? At some point P, let's suppose this is the point P, we want to find the magnetic field, right? What we'll do is that we'll just draw this, we draw a closed line here like this and enclose the current, right? We're enclosing the current here. This is the current enclosed. So you can see here only few currents are enclosed inside this closed path, right? I6, I5, I1, I2 are the currents enclosed, right? And I3, I7, I5 are the current outside this loop, right? Definitely now some currents are flowing into the loop, right? And some currents are actually flowing out of the loop, right? It means that we'll be actually calculating the net current, right? We'll be calculating the net current which is into the loop, right? And the current which is outside perpendicular to the loop, right? Or we can say the current into the loop or current out of the plane of this loop, right? So let's suppose if we represent this current I1 as plus I1, then definitely we have to represent this current I2 as minus I2, right? And this current I4 as plus I4, right? And this current I6 as minus I6, right? So if we apply the Ampere's circuital law for this loop, then integral of P dot TL will be equal to mu naught I enclosed. I enclosed will be I1, right, plus I4, I6 and I7, right? I6 and I2. I7 and I3 currents and I5 currents are not enclosed by this loop. So this will be the net magnetic field at this point P, right? Or we can say this is how we can apply the Ampere's circuital law, right, for this loop. And for different symmetric systems, right, for different symmetric systems, actually, it's a very handy tool, very important law to calculate the magnetic fields due to different symmetric current distributions, right? Due to different symmetric current distributions, right? And for this distribution also, the Ampere circuital law is definitely valid, right? It's still valid, but will not be able to take this b term here from this integral outside this integral, right? Will not be able to take out this magnetic field term from this integral so as to calculate the magnetic field at some random point p, right? For that we need to have a symmetry, right? So let's try to understand the different symmetric objects and try to calculate the magnetic fields for them, right? And most important point about the Ampere's circuital law is that we apply this law for the calculation of magnetic field if the currents are actually a constant or the steady currents, right? The currents should be a steady or the constant currents, right? And we apply this law actually to calculate the magnetic field for symmetric distributions only, right? For calculation of magnetic field. But it doesn't mean that this application this law will not be valid for uh, asymmetric or the system which is not symmetric with respect to the current distribution, right? It will be still valid, but we will not be able to take that magnetic field term out of the integral and will not be able to calculate the magnetic field, right? Uh, so we can actually apply this Circuital law, irrespective of the shape of a loop, right? Shape of a loop can be anything, right? But if the loop is symmetric, then it becomes very easy, quite easy for us to calculate the magnetic field, right? Now let's try to calculate the magnetic field because of this infinite thin wire, right? Magnetic field because of this infinite thin wire. So this is a infinite thin wire here. The current I is flowing through this infinite thin wire, right? Current I is flowing through this infinite thin wire here. Let me take it here. So current I is flowing through this infinite wire. We have to apply the Ampere's circuital law to calculate the magnetic field, right? At some point R, right? Let's suppose this is the point R. This is the point R. We want to find the magnetic field at some point R. So what we'll be doing is that we'll just draw this Amperean loop, which will be a circular here, right? It will be a circular loop here, right? It will be a circular loop here because on the surface of this, on the circumference of this Amperian loop, on the circumference of this Amperian loop, the magnitude of the magnetic field will be actually same at each and every point, right, on this Amperian loop, right? So that's what we say by the symmetry of this loop, right? Because at each and every point on the circumference of this Amperian loop for this infinite line current distribution, right, the magnetic field will be a constant in magnitude, but the direction of the magnetic field will be definitely different at different points on this circumference, right? In the same manner, when we applied the Gauss law, right, for the calculation of the electric fields, then at that time, let's suppose we had taken the sphere as a Gaussian surface. Then on the surface of that sphere, on the surface of that Gaussian surface, the electric field was a constant in magnitude at each and every point on that Gaussian surface. But the direction of the electric field was different, right? So similarly here at each and every point on this Amperian loop, the magnetic field is a constant here, right? Magnetic field is a constant, but the direction of magnetic field is different at different points. Or we can say that magnetic field is a constant in magnitude, but not uniform field, right? Magnetic field is not uniform here, right? So if we say the magnetic field is a uniform, then it has to be constant with respect to direction as well as magnitude as well. But the direction of the magnetic field on the Amperian loop will be different at different points. Let's apply the Ampere circuital law on this loop, right? So we'll use just integral of P dot dl, right? P dot dl. That will be equal to mu naught I enclosed. You can see that total current enclosed by this Amperian loop for this thin wire is I. Now we have to calculate this dot product here, right? You can see here, we can see if we take this length element, right? If we take this length element dl, dl is the length element, or we can say that this is a length vector, right? Elemental vector here, dl vector. And this is the direction of this dl vector. So the direction of this dl vector is actually along the direction of this current, right? So current is actually moving upwards. So the direction of this dl vector will also be taken as upwards, right? Now we have to find the magnetic field. Let's suppose this is the point P where we have to find the magnetic field, right? And you can see that at this point P, the current is actually perpendicular to the plane of this Amperian loop. If the current is perpendicular to the plane of this Amperian loop, then definitely this dl vector has to be perpendicular to the magnetic field at this point P, right? Or we can say that cos of theta, that's P dot dl. If we calculate P dot dl, that will be equal to B dl cos of theta, right? B dl cos of theta, right? It will be P dl cos of theta, right? Correct. So if this is P dl cos of theta, then this dl angle between this dl and magnetic field here, right? You can see angle between this dl here and the magnetic field is actually a 0-degree angle, right? It is a 0-degree angle. So putting the theta equal to 0 in this equation, right? So our B dot dl actually comes out to be equal to B dl, right? B dl. So we can substitute this in this equation, right? We can just take B outside this integral now, because B is just a scalar, is a magnetic field is just, now dot product has been calculated. We are left with the magnitude part of this B only, right? We can just take that outside this integral, right? We're now left with closed integral of this dl, right? That's mu naught I. Now this dl is nothing, is the length element, right? This is nothing, this is the length element of this Amperian loop, right? Length element of this Amperian loop, right? Length of element of this Amperian loop. Now, if we calculate the length, total length of this Amperian loop, it will give us the circumference of the Amperian loop, right? So circumference of this Amperian loop is nothing, that's the 2 pi r, right? 2 pi r, or we can say that that will be equal to mu naught I, right? Or magnetic field here will be equal to mu naught I upon 2 pi r. So this is how we apply the Ampere's circuital law to calculate the magnetic field, right? So it means that each and whenever we choose an Amperian loop, we have to do all the calculation on the circumference of that loop, right? We have to do all the calculation on the circumference of that loop. We have to check the direction of the length element of that Amperian loop with respect to the magnetic field because of the current element, right? We have to find the direction of the magnetic field, and then we have to find the direction of the magnetic field vector with respect to the length element vector of that Amperian loop in order to find the total magnetic field, right? So this is how we applied the Ampere's circuital law for this case. That's the magnetic field due to thin wire, right? Thin infinite wire, that's mu naught I upon 2 pi r, right? Now let's suppose if we have this case, right? If it's a thick wire, right? If it's a thick wire here in this case, if it's a thick wire, then what we have to do is that we'll just apply the Ampere. We will just apply circuital law twice now, because inside this thick wire, the current enclosed by this Amperian loop will be different than the current enclosed by the Amperian loop outside this wire, right? So we'll be applying the, in that case, we'll be applying the Ampere's circuital law twice, right? Two times. And then the behavior of the magnetic field will be different outside the thick wire, and the behavior of the magnetic field will be different than outside, and it will be different in inside also, because the distribution of the current will be different for outside and inside also. So we'll be discussing that further in the next lecture, right? So time is already over. Let's discuss it on Monday, right? For the calculation of the magnetic field for different distributions, right? So let's stop here. We'll meet in the next lecture on Monday. Till then, take care.